everybody. We are back and talking about the second half of our intermolecular forces that you could potentially see. There are two more that we need to talk about, and the next one are what we call dipole to dipole forces. Now, you should know the word dipole. Dipole means polar. So a dipole to dipole interaction is something that's present only in molecules that are polar. And that's why it's so important that you know how to identify a polar molecule, because if you don't know how to do that, you can't identify dipole to dipole forces. So what ends up happening is in a dipole to dipole force, there is an attraction between a molecule that is polar and another neighboring molecule that is polar. So it is the partial negative charge of one molecule sticking to the charge of a partial positive to the other. And you say to yourself, is that not exactly the same as a London dispersion force? And the answer is, the general principle of it is the same, but what makes a dipole to dipole intermolecular force stronger is that the polarity isn't temporarily caused by that little flip in electrons. It is a permanent partial negative and partial positive on your molecule that are causing the intermolecular force. So what ends up happening is in a dipole to dipole intermolecular force, there are a couple of different things that can affect the strength of that. The first is the polarity of that molecule. So in certain things, if you have, let's say, a mix of polar bonds, if you get more polar bonds, generally, you end up in a situation where you have a stronger dipole to dipole intermolecular force. There is a tipping point with that, though, and that is when you have so many polar bonds that your molecule actually becomes not polar. So you got to be careful for that. So just keep that in mind. But otherwise, in general, if you get more polar bonds, you're going to have a stronger dipole to dipole interaction. And so that's especially in big molecules where you have maybe 3 or 4 different areas that are polar. That's going to make a really big impact on your intermolecular force strength compared to something that has only one polar bond as well. The other thing is if you get a very polar bond, you will also see a stronger intermolecular force for that as well. This is hydrochloric acid, HCl, as our example. So it is a covalent bond between H and Cl. And if you find the difference in electronegativity, Cl is, I think off the top of my head, I want to say it's a 3.0 and H is a 2.1. So there is a difference of 0.9. The partial negative charge goes onto the chlorine here because the chlorine has the higher electronegativity value, and the partial positive lands on the hydrogen because hydrogen has the lower electronegativity value. So hopefully that's a review for you. But what ends up happening is that the negative side of one HCl is attracted to the positive side of the other HCl. And the reason why this is stronger than a London dispersion force is because this is a permanent situation. So this partial negative will always be on the chlorine, and the magnitude of the negative and positive are always going to stay the same. In a London dispersion force, it's really temporary and it kind of flips back and forth, and so it's not quite as strong. So the intermolecular force is this dotted line, that attraction between the two. And it's not dissimilar to a magnet. So if we take a look at, I've got 2 little waters here, okay? So water, we know O in the middle is the red, H is the white. If you think about an O to H bond, O has a high electronegativity, H has a low electronegativity, and so when we think about the polarity of an O to H bond, we end up with a collection of negative charge up at the top here and positive charge here. And because of water's bent shape and those unshared pairs on the central atom, we get a polar molecule. So keep in mind, the white is partially positive. If I look at how these are attracted to each other, the partial negative of one is attracted to the partial positive of the other. And the intermolecular force is that magnetic attraction that you are seeing there, okay? So an intermolecular force, again, is between 2 molecules. It's not the bond that you are seeing. The last intermolecular force and the strongest of them are hydrogen bonds. Now, hydrogen bonds are like dipole to dipole intermolecular forces on steroids. This is the best way I can kind of explain it. So they make things stick together probably stronger than you think they should. And it's a very special circumstance, and it only occurs in substances that when you draw their Lewis structure, they have an F connected to an H, an N connected to an H, or an O connected to an H in the physical Lewis structure. However, the bond itself is not the hydrogen bond. It causes the hydrogen bond, but in and of itself, it is not the hydrogen bond. And like I said, it's the strongest of those forces. Now, the reason why hydrogen bonding is so strong and so unlike the rest of them is that it is a very polar bond because you're dealing with elements that have high electronegativity. So it only happens in elements that have H connected to F, O, and N. And those are some of our highest electronegativity elements on the periodic table. That, coupled with the tiny size, and we talked about how attractions between elements that are very close to each other give us strong bonds. So, and I'll show you a picture of kind of what happens. That tiny size allows neighboring elements and molecules to get very close together, and then they form a very strong attraction. So here is water again. Water is probably the most common thing we talk about because its properties happen because of the hydrogen bonding. So if you look at the Lewis structure for H2O, H2O has an O to H bond, okay? That is a very polar bond. It's got a difference in electronegativity. I think of like, 1.4. So it's pretty big. O is partially negative. H is partially positive. These are very tiny little atoms here. So what can happen is I have a very polar bond in my water, and it's very tiny. So what it can do is it can attract and get really close in tight to the hydrogen of another water next door. And that close proximity is kind of like Coulomb's law. Again, it's not a bond, but it's a very strong attraction to its neighbor. So the O to H connection causes the hydrogen bond next door, if that makes sense. You also could have an N to H here or an F to H, okay? And again, this is just kind of a rendering of water like the molecules that we saw. So the partial positive charge on the hydrogen is attracted to a partial negative on the other side. They are going to ask you to be able to draw pictures like this to explain intermolecular interactions. And we are going to practice that so you'll get the hang of it, okay? So nothing to stress about, but we will get some practice with that. This actually plays a really interesting role in DNA. So I am confident that you've taken a biology class where you've talked about A and T that go together and G and C that go together. And the reason why they are the ones that match together is actually because of their opportunities to hydrogen bond. So if you look at guanine and cytosine here, they have an N to H in guanine in 3 different locations. I have a N to H here, an N to H, and an N to H. And in cytosine, I have the same kind of thing where I have N to H connections. So these sites here are places where we can have a hydrogen bond potentially form. What happens in the case of these 2 pairs in DNA is that the hydrogen bond in one is attracted to a polar bond on the other molecule. So you can look at this one up here for guanine and say, hey, this is not a hydrogen bond, right? This doesn't have the O to H. However, the N to H here is attracted to this O and can form a hydrogen bond. Same thing here and same thing here. The adenine and the thymine does the same thing. So I have an attraction in 2 places, and that's why they fit together instead of the 3. Okay? Excuse me. So in a previous presentation, I had asked you to draw 3 Lewis structures, and we are going to now identify the intermolecular forces that go with that. So give me 1 second. We're going to take a look at your Lewis structures and see if we can identify the intermolecular forces. Okay, so to start off, number 1 is CH4. It's methane. You've probably heard of that before. This is the Lewis structure for CH4. So when I go through Give me 1 second. Come on. Oh dear. Thank you for your patience. I'm about to screw this up. There we go. All right, so back to our examples here. You should have drawn the Lewis structures for these, but now we want to identify the intermolecular forces. So the first thing we understand is if we look at this Lewis structure and I can draw a Lewis structure for it, the first thing we know it has is London dispersion forces, which we can abbreviate as LDF, okay? Then I check to see if these bonds are polar. And in the case of CH4, the bonds are not polar. So that rules out dipole to dipole and hydrogen bonds. So that means my intermolecular force, the only one that I have in CH4 is a London dispersion force, and that's it. Okay. If I take a look at CH2O, automatically, because I can draw a Lewis structure, it has London dispersion forces. Now I need to take a look at the bonds and see if I have a polar molecule. C to H we know is nonpolar. O to C is a polar bond. O has a partial negative. C has a partial positive. Because we have a blend of types of bonds here, that means that this is a polar molecule. And that means that we have dipole to dipole, which I'm going to write DD there, okay? The dipole to dipole force is stronger than the London dispersion force in this molecule. Next thing we need to do is we need to check and see if it can hydrogen bond. This connection here, O to C, is not able to hydrogen bond. And since this is not a C, or because this is a C and not an N, an O, or an F, we cannot hydrogen bond here. So the only ones we have are London dispersion forces and dipole to dipole. Lastly, we have CH3, part of my scribble there, OH. This is the correct Lewis structure for that. If we look, we can draw the Lewis structure. So it has London dispersion forces. If we do our bond analysis and we look, it has a C to O, which we know is polar. Partial negative on the O, partial positive on the carbon. The O to H bond is also polar. The same charge distribution happens where the electrons head to the oxygen. And so since we have the mix of bonds here, that means that this is polar and we have dipole to dipole. And then lastly, in this case, because we have an O to H connection here, this can hydrogen bond with anything else. So I have a hydrogen bond here as well. Again, this is not the hydrogen bond. This is the place where it can form a hydrogen bond with something that's capable of doing that. Okay? So your homework is going to ask you to do this same process. If you see something that can make a hydrogen bond, it can make the rest of them. But you have to go through and figure out the process. If you find yourself having any questions, we'll get things cleared up as soon as possible. All right, good luck.